morning to all. So, we are discussing unit number 3, that is process synchronization or the concurrency control. So, in the yesterday's lecture, we have discussed about the process synchronization. That is how the process synchronization, what exactly is the meaning of process synchronization, and what is the need of process synchronization. So, as there are, as you know that there are n number of processes they are running in the system, right? So, and the resources are limited. To acquire the resource, there may be a race condition arise between the process, or there may be a competition start between the processes. And to avoid this competition, to avoid this particular race condition, the synchronization must be there. There must be a proper synchronization, or there must be a proper process communication or the coordination. So this thing is achieved with the help of your critical section problem. So critical section is the section which is common to all, or one can say that the critical section where the one can say that the shareable resources are kept in the critical section. For example, any file that is being shared within multiple number of processes, it is kept under the critical section. Or say for example your main memory, it is also kind of critical section. So because it is accessed by other process, so we can say that critical section and the critical section works on the rule of mutual exclusion. So what is mutual exclusion? So mutual exclusion is nothing but when one process is accessing in its critical section, no other process is allowed to enter into the critical section. That is called as the mutual exclusion, right? So so processes must be mutually exclusive to have access to the critical section, right? So in this case, when process is executing in the critical section, means it is changing the common variable, it is updating the common tables, it is changing the common information. So at the same time, other processes, they have to wait. That is nothing but the critical section. And the concept of the critical section is implemented with the help of, one can say that, with the help of semaphore. So semaphore is nothing but your integer value, or it is one integer value. And a semaphore is implemented with the help of two functions, that is wait and signal function. So wait function is decrement the semaphore value by 1, whereas the signal function increment the semaphore value by 1. So wait and signal, they are the same just as of your green signal and yellow traffic light signal, right? So if the process executes the wait function, so wait, by executing the wait function, the current process telling to the other process, yes, I am executing in the critical section, you have to wait, right? And once it is completely executed in the critical section, once its work has been completed, then it gives the signal, means it gives the green signal to other process, yes, now I am leaving the critical section, now you can enter into the critical section. It is a simple logic, and it is implemented with the help of your semaphore. So we have also seen one example. So problem, it is called as example, or one can say it is nothing but one method, or it is nothing but one type of the synchronization. So one type of the synchronization means there may be the reader type of processes, or there may be a writer type of processes, right? There may be producer and the consumer type of process. So we have seen that one. So producer processes as well as the consumer processes. So what is producer process? So producer are the process, they go on producing the things that can be consumed by the consumer process. And which is the shared resource here? This particular one can say this buffer is nothing but the shared resource here. So buffer is shared resource in the sense that, so means if the two types of process, so there are, say for example 100 producer processes and there are 100 consumer processes, right? So if this kind of processes, they want to access the shared, and there is a single buffer, and if these processes want to execute that particular buffer, or they want to access that buffer, then there must be mutual exclusion. So the condition which are being implemented, the condition which are being enforced, that are nothing but the producer must not override a full buffer. This is the first condition, first restriction put on the producer process. The second condition put on to the consumer process, that consumer must not consume the empty buffer. And the third condition, which is put on both producer as well as the consumer, they must not access the buffer. They must access the buffer in mutually exclusive manner. They must access the buffer in mutually exclusive manner. Means when the producer is producing and go on putting the item in the buffer, the consumer has to wait. And when consumer is consuming the item from the buffer, then producer has to wait. Producer do not access to that particular buffer. So this is the way we have seen yesterday, this particular one example, or this is one type of the how the synchronization is achieved, how the communication is achieved within the producer and the consumer types of processes. Getting my point? So pseudocode, we have also seen the pseudocode, that is the producer process and the consumer process. So there are three semaphore actually we have declared here. That is nothing but the mutex is the mutual exclusion between the producer and consumer. One semaphore is this empty is for your producer, and semaphore full it is for consumer process. And initialize empty n is equal empty is equal to n, and full is equal to 0. And we have written this particular code, we are executing this particular producer and consumer problem. The next problem which we have to discuss today is nothing but your reader writer process problem. So reader writer process problem, in the sense that there are, see carefully, there are processes, they are of the type of reader processes, and there are some processes they are of the kind of writer processes. So meaning is that data area shared among the number of processes, it could be a file or it could be a block of main memory. So definitely the processes want to write data into the file, as well as the processes, they must want to read that particular file, right? See, for example, if this is the file, if I assume that this particular is the file, and there are, say for example, this is the reader process, this is reader 1, this is reader 2, reader 1, reader 2, and reader 3 process, right? And there are writer process, writer 1, writer 2, and writer 3. So this is another category of the processes. See carefully, yeah, means first category we have discussed, that is nothing but the producer and the consumer type of the processes in the system. The second category is nothing but the reader and the writer types of process. So meaning is that, so number of processes that only read the data, they are called as the reader, they are called as the reader processes. And the processes that only write the data, they are called the writer processes. So writer are the processes, these are the writer are the process, they are able to write the file, they are able to write into the file. Means they can edit the file. Yes, the writer process, they are able to edit the file, they can write the file. And the reader are the process, they are not able to write the file, but they only read the file, they are only able to read the contents which are written inside the file. So this file, so one can assume that this file is nothing but your shared resource, SR. I can write here, SR stand for your shared resource. So file is nothing but the shared resource, right? So again we'll consider the critical section. So put this particular shared resource or file in the critical section, and we have to implement the reader writers problem also with the help of our critical section. So how? So following condition must be satisfied. So if there are multiple reader processes and the multiple writer processes, and they want to access the same file, they want to access the same resource, then how the synchronization is achieved? What is the problem statement? See carefully once again. If there are multiple reader processes and the multiple writer processes, right, and there is a single file which is to be shared between the writer and the reader processes, then how the synchronization between the reader and the writer processes can be achieved? That is the question, or that is the problem task. So this task is solved with the help of synchronization. How the synchronization is achieved? So first we have to enforce the restriction on the reader process. So any number of readers may simultaneously read the file. This is the first condition we have to implement. Meaning is that, because there is no question about the editing, these reader process, they are not going to edit, they are not going to write, they are not going to modify or change the content of the file. They just go on reading. So you can allow multiple number of reader processes to read the same file. The first condition. Second condition is for writers. So only one writer at a time may write into the file. This is the second condition. Because writer processes are now able to edit, or they able to write the content into the file. So only one writer process is allowed to enter into the file, or only allowed to execute that particular file so that it can write into the file, right? And the third condition is between, again, writer and the reader process. So it is between writer and the reader process, similar to your producer and consumer. So in the earlier case, the first condition is put on for the producer, second condition is for consumer, and in third case is put on both for the mutual exclusion between producer and consumer. The same case here, the first condition is put on reader, the second restriction is on writer, and the third restriction is put on the both. That is, if writer is writing to the file, no reader may read it. Meaning is that reader and writer, these are mutually exclusive. This statement is important. So reader and writer process, they are mutually exclusive in nature. Means when one writer is writing into the file, readers are not allowed to read that particular file. or when reader are reading that particular file, the writer processes are not allowed to write into the file. The reader writer process, if these two kind of processes, they are mutually exclusive. So I can have there, this is called as the mutual exclusion between the reader and writer process. However, the first condition is true. Number of writers that can be allowed. There are 10 writers. There are number of readers that can be allowed. That is number of readers, maybe 10, 15, 100 number of readers. They can simultaneously, concurrently read the file at a time. Right, but there are restriction on number of writers. Only one writer at a time is allowed to write into the file. Getting my point? So this is the way how the synchronization, how one can say the concurrency is achieved within the reader and the writer type of processes. Right. See here. Now we can have the pseudocode for the reader as well as the writer process. So mutex, mutual exclusion between the reader and the writer process. The first semaphore is declared to 1. WRT is the semaphore, mutual exclusion between the writer also, because there must be mutual exclusion between the writer, because no writer is allowed. When one writer is writing the file, other writer have to wait. So the WRT is the semaphore that is for the writer processes only. And there is no semaphore required for the reader, because any number of reader you can allow. And the read count is nothing but it keeps track of how many processes are currently reading the object. Means it is nothing but the read count means how many reader processes are reading that particular file. So variable that is mutex and WRT semaphore, and read count is the integer. So this is nothing but your declaration part before writing to the pseudocode. Always there is a question in the examination: write the pseudocode or implement the reader writer problem by semaphore, or implement the reader writer problem using semaphore and write the pseudocode. So you have to write the pseudocode correctly. You have to first declare the variable. So understand the concept first, na. So reader writer, how the synchronization is achieved with the help of this particular semaphore. So this is the thing. Reader processes are there, writer processes are there. So any number of readers can read the file simultaneously. The only one writer is allowed. So there is a mutual exclusion between the writer also, and there is a mutual exclusion between reader and writer also. Because if writer is writing, readers are not allowed to read the file. And if the reader are reading, writer is not allowed. Means writer process has to wait. Clear? So pseudocode is for the writer process is nothing but the wait WRT. Writing is for form, and a signal WRT means what we are doing here. We are decrementing the WRT count by 1, and this is the writer process. This is the code for the writer process, and the code for the reader process or pseudocode for the reader process is wait mutex. Means initially wait mutex, first execute the wait function on this mutex semaphore, then read count equal to read count plus 1, because this is the reader process and you can have multiple number of reader process. So for writer it is only 3-line code, but for reader the code is in this way. If read count is equal to 1, then wait WRT and signal mutex, then reading is performed, because multiple number of processes they go on reading that particular file simultaneously. Then wait mutex means again the mutex semaphore is executed with the help of wait function. The read count equal to read count minus 1, and if the read count equal to 0, then signal WRT and signal mutex. Means we have to associate this reader and writer process with the help of these two semaphore, that is mutex and WRT. So if writer executes signal WRT function, then we may resume execution of the either of the waiting reader and or single writing writer process. Getting this point? So this is the logic behind the pseudocode of the writer and the reader process. This is the way. Clear? So if you have a doubt, you can ask me. Now the next example of the process synchronization is the dining philosopher problem, or it is you cannot make it as a word problem, but it is nothing but an example. Dining philosopher is another example of the process synchronization, and how this process synchronization is achieved with the help of your semaphore. Again, you have to solve this problem, or again you have to write down the pseudocode with the help of semaphore for solving the dining philosopher problem. Or it is another kind of the processes. Means there are some processes in the system, they are of the type of dining philosopher nature. There are some processes in the system, they are of the type of reader writer in nature. There are some processes in the system, they are of the type of producer and consumer processes. Getting this point? So what is the dining philosopher? Let us see. So assume that 5 philosophers sit around a circular table. The table is shown here in the figure, and this P1, P2, P3, P4, and P5, it represents the philosopher. philosopher means generally these people, they go on thinking and they are putting some theories, they are putting some logic. Philosopher, right? So each philosopher spend his life alternatively thinking and eating. In center of table is a large plate of food. So here so food is also shown here. A philosopher needs 2 forks to eat a helping of food. To eat a helping of food means to, so philosopher P1, suppose P1 want to eat the food, then it has to take the fork, this number 2 and fork number 1. Because without taking this two fork, or one can say spoon, for simplicity in our language we can say it as a spoon. So for to eat the food, it has to take the 2 spoons which are situated at the left hand side and the right hand side of each philosopher. This is the scenario. Next one. One philosopher, one fork is placed between each pair of the philosopher, and they agree that each will only use the fork which is immediate to right and left. Means the philosopher must pick up the fork which is situated immediately left and right hand side. They will not go to some other spoon or the fork which are put on the table. The problem is, now what exactly is the problem? So problem is to design a set of processes for philosophers such that each philosopher can eat periodically and none dies with hunger. When one philosopher is eating, philosopher to the left or right cannot eat since forks are shared resources. Now clear this thing. So P, so you can call it as a philosopher, or in terms of our operating system, we are calling it as a process. So there are 5 processes: process number P1, process number P2, and process number P3, process number P4, and process number P5. 5 processes, or you can call it as a philosopher. And between process P1 and P2, there is a 1 fork, or there is a 1 spoon. Between P2 and P3, there is a 1 spoon, and between P3 and P4, there is a 1 spoon, and P4 and P5, there is a 1 spoon. That is, this is called as a resource. This is a resource. Say for example, this is resource 1, this is resource 2, this is resource 3, and resource 4, like this way. And resource 5 is between process P1 and P5. We are calling it as R5, or we can call it as a spoon, or we can call it as a fork. The condition is that when the process P1 want to execute, it can use the resources which are situated near to it. That is nothing but 1 and 2. It cannot go to 3 or 4 or 5. And we have to also ensure that all processes must be executed. Meaning is that neither of the philosopher dies with hunger. Meaning is that all processes must get chance to execute that particular resource, to use that resource and to execute that resource. Getting this point? So meaning is that when the philosopher, if P1 is trying to eat the food, so it has to pick this particular fork 1 and fork 2, or spoon 1 and spoon 2. So at the same time, this P5 philosopher or P5 process or P2 process, they have to wait, because they don't have a fork or they don't have a spoon to eat, right? So this fork or spoon are nothing but your shared resources. This fork number 2 is shared between P1 and P2, 3 is shared between P3 and P2, the 4 number is shared between P4 and P3. So as these are the shared resources, they have to wait. Means it is nothing but your critical section. So you can say this fork 1 or spoon 1, spoon 2, spoon 3, all these are nothing but the resources, and they are called as the shared resources. SR stands for the shared resources. Getting this point? So we have to try that the processes, when P1 is trying to execute that particular resource, trying to use that resource on its left and right side, the P2 and P5 has to wait. When P5 is in a running state, meaning is that when P5 executes, so it will take this particular fork and this particular 1 and 5. So at the same time, P1 has to wait and P4 has to wait. Getting my point or not? See carefully. If P3, so for example, P3 is in a running state, process P3 is now in a running state. So for execution for P3, it requires this fork number 4 and fork number 3. So P2 and P4, they have to wait, because they cannot use this 4 and this P2 cannot use this 3 number spoon. Getting my point or not? So as soon as the P3 completely finished, it will put down this fork 3 and 4, so that the P2 and P4, they can start their execution. Right? Means all the processes, they have to follow the semaphore signal. They have to follow the wait as well as the signal function. So if they are in a running state, they have to wait. They have to execute the wait function to P2. Suppose P3 in a running state, it will execute wait function to P2 and wait function to P4. They will send the signal that yes, now I am using that particular resource. You have to wait till I complete my execution, right? And as soon as it will finish its execution, it will put down this fork and it will give the instruction, or it will execute the function signal. It will change the semaphore value and giving the signal that yes, now these resources are free. You can use that resource with the help of critical section. Getting the point or not? So this is the way. So there are 5 philosopher process number 1 to 5, or you can call it there are 5 processes 1 to 5. Between each pair of philosopher is a fork. Fork is number 1 to 5. So for example, fork number 3 is between philosopher number 2 and 3. So each philosopher alternates between thinking and writing. Using semaphore, we can solve this problem. We have already discussed this. So each philosopher picks up his right fork before try to pick up his left fork. So represent each fork by a semaphore means this particular fork is represented by semaphore. A philosopher tries to grab and release his tries to grab the chopstick or the fork by executing the wait function, wait operation on that particular semaphore, and release his fork or chopstick by executing the signal operation. Means if the particular process P2 want to execute this 3, means it will execute, it will send the, or it will execute the wait function, right? And as soon as you release this third number 4, it will use, or it will execute the signal function here. Getting my point? And so this is the pseudocode is given here. See, for example, chopstick array 0 to 4, it is nothing but the semaphore, because we have semaphore 1 to 5 semaphore. So you have to take the all the semaphore value and the wait function for the semaphore and the signal function for the semaphore. So array of the semaphore is taken here. Array of the semaphore is taken here. This is the pseudocode for the dining philosopher problem. This is the way how we can solve the dining philosopher problem with the help of our semaphore, right? So clear to all of you? I think there may not be any doubt, but if you have still any query, so you can ask me. So we have seen the 3 classical examples of the synchronization. So the main intention or the main aim behind this is that we have to understand the synchronization correctly. So how if there are multiple number of resources are there, and if the multiple number means here we are using multiple number of semaphores. Here we are using array of semaphore. Array 0 to 4 means there are 5 semaphore, right? And in case of earlier reader writer, or in case of producer consumer, there is only a single semaphore we are using because there is only one shared resource. But here there are 5 shared resources between the 5 different processes, right? Processes are more as well as the resources are more, and that is another category. We can define it as category of the processes in the system, and that particular category problem we can solve with the help of this dining philosopher logic. This is exactly the logic behind that particular thing, how to solve. If such a situation arises in the system, how we are going to achieve the synchronization, how we are going to achieve the concurrency. So problem, the answer is given by this particular problem. So problem is, it is actually the answer to the situation. If this is the situation, so we are using this particular thing, right? So we are solving the particular problem, we are solving the situation, we are handling the situation with the help of such solution. The dining philosopher is one solution. So reader writer is another solution, and the producer consumer is another solution. So this is nothing but the exact actual concept of the process synchronization. So up till now we have seen the process synchronization, how the synchronization is achieved with the help of critical section. And critical section means what? How the critical section is there, and then semaphore, wait function, and the signal function. Then 3 problems we have seen. Now we'll start, or we'll go to the next topic. Okay, so the next topic in this particular 3rd unit, it is called as the deadlock. So in this today, we are just going to see the introduction about the deadlock. So what exactly is the meaning of deadlock? So everybody, I think you all of have your laptop or your desktop with you, right? So it may happen that while working on the laptop or on desktop, it may happen that sometime your laptop may get hang, right? Or your desktop may get hang. So what do you do generally when your laptop get hang? You put Control Alt Delete, the window of end task open, and you are forcefully ending some task, right? And when some task or when processes are closed forcefully, then your laptop or the desktop will again regain its original state, right? So this hang condition, or when one can say that when the laptop get into the hang situation, the neither of your keyboard work or neither of your key or neither of your command work, whether you give the command with the help of your mouse or whether you give command with the help of your keyboard, it won't work. It won't work. Why? Because the system is in a hang situation. Means your operating system, laptop get hang or the desktop get hang, means what your operating system is in a hanging state, means it could not go further. It could not process. Neither of the process can do its useful work, and we are saying it is in a deadlock state. So hang state, the day-to-day work, but practically or technically, in terms of operating system language, we are referring this situation as a deadlock. So we are referring this situation as a deadlock, and we have to deal with the deadlock scenario. We have to deal with the deadlock scenario. We have to see which are the necessary conditions. Then we have to see how to avoid the deadlock. Then we have to see how to prevent the deadlock and the algorithm to avoid this particular deadlock. That we have to see. So in case of, see the theory, in case of multi-programming environment, several processes compete with finite number of resources. As everybody know that there are n number of processes and there are only very few number of resources, and definitely there is a competition, there is a race condition, and to avoid the race condition, we are using the synchronization. Okay, a process requests resource, right? If the resource is not available, the process enters into the wait state. Everybody know this. The process, for its complete execution, it requires the resources, and if that particular resource is not available, why? Because that resource is busy with some other process, then that particular process has to wait. The requesting process has to wait there. It may happen that process never get the resource because of the resources held by other waiting processes. So it may happen in the system. So see the scenario. This situation is called as the deadlock state. This situation is called as the deadlock state. So see the example. For example, if there is a resource, for example, this resource R1, right? And this resource R1, it is now being used by, suppose, say, for example, process P1, and there is another process P2 that require that particular resource R1, right? But as this resource R1 is already engaged with this process P1, the resource R1 cannot be given to the process P2. So P2 is in a wait state. So P2 is in a wait state. See carefully, yeah. So P2 is in a wait state. So assume that there are 100 processes. For example, for simplicity, we assume that there are 100 number of processes in the system, 100 number of processes, right, there in the system. So initially, there are 10 processes, they are in a waiting state. They are in a waiting state, no problem. And the 90 processes, 90 processes, they are in a running state or they are in execution state, no problem. The system will work. And why these 10 processes are in waiting state? Because this is the same scenario like this P2. They are same as that of that P2 process or process number 2, because they are waiting to get the resource, but that resource has been engaged by some other process, right? So now the scenario changes. As the time passes, the scenario changes. The 50 process, now they are in a waiting state, and the 50 process, they are in a running state, for example. So the percentage of, see the percentage of running process here, percentage of running process, initially 90% processes are in a running state, execution state, and only 10%, only few processes, they are in a waiting state. The amount is very negligible. Now as the time passes, the number of waiting processes increases. So 50% processes, they are in a waiting state. They are similar to your P2. They are waiting to get that particular resource, and they could not get the resource because that resource has already been assigned to some other process, which are in a running state, right? Again, after some time, the scenario changes, and it may happen that there are 90 processes, they are in a waiting state, and only 10% processes, they are in a running state, for example. What is the scenario? The 90% process or 90 process, they got into the waiting state, they stuck up. They could not process further. They could not run successfully. Why? Because they are not getting the resource for their execution. So they enter into, so percentage of waiting processes is getting increasing after some time, and the percentage of running processes, it is getting decreased as the time passes. So if this situation is there, so we can say that the system enters into your deadlock state. This is the deadlock of your system. This is the complete deadlock of our system. Means very few processes they run in the system, and there are 90% processes they are in a waiting state. Waiting state means what? They are not in a running state. Waiting. What is the meaning of waiting state? They are not in a running state. They are waiting. They could not perform the useful work. They could not perform their task. So, and the running process, they only 10%, only few processes, negligible amount of processes, they are in a running state. That is of no use. And we are calling this situation as a deadlock, or in our day-to-day language, you are calling it as the system get hang. So, operating system get hang, meaning is that there are the processes. The percentage of waiting process is much more as compared to percentage of running processes. So, what is the solution you are doing here? The solution, you are putting Control Alt Delete. You are pressing Control Alt Delete. The task manager window get open here. And what you are doing, you are forcefully ending the process, or you are forcefully killing the process. So that particular process get killed. So what you are doing, what you are killing the process means what? You are stopping the execution of some of the process. And as soon as you stop the execution of the some process, as soon as you kill the process, the resources, see carefully, the resources which has already assigned to that particular process now get released. And as soon as these resources get released, these processes, they get their resources, and the system again regain the state, again get into the working state. Getting my point or not? What is the scenario? As soon as you kill the process, as soon as you stop the working of the some process, you are putting the end task, right? So what is this end task? So end task tells you are putting this end task. So just do at your laptop or desktop. Means you can without hang situation also, you can execute the command. You just put Control Delete, and you just end task some of the process. That process will be terminated. You are terminating the execution of the process. So when means you are forcefully stopping the execution, and when you are forcefully stopping the execution, so meaning is that the process get terminated, and the resources. So we are more focused on the resources which are already allocated to that particular process. Now that are being released. And as soon as these resources get released, so the process that are in a waiting state, they get the resources. And as soon as they get the resource, the system again get into the proper working condition. Right? So this is the way how we are dealing with this thing. But the problem is that we have to ensure that we, in the sense operating system, it is the responsibility of operating system that system must not enter into the deadlock state. Right? So deadlock is the final step. So operating system has to ensure that the system must not go into the final step. It never enters into the deadlock state, never forcefully terminate the processes. Right? So how to deal with the deadlock? How the system will take care? So prevention is always better than care. That is the said. So how the operating system take the preventive measures, that we have to see step by step. So see here. So normal mode of operation of the process, one can say request. If the request cannot grant immediately, the requesting process must wait. So process may request the resource use. If the process is using that, process can operate on the resource, means process is currently using that particular resource, and release. The process release the resource. The three mode means three terminology we have to remember here. The request, the process is requesting certain resource. The use means process is currently using that particular resource, and release. After using, the process may release that particular resource. That is the three terms. The type of the resources, there are physical resources and the logical resources. Everyone know printer, tape drives, memory, CPU, secondary storage, etc. They are called as the physical resources, and the logical are the file, semaphore, monitor, etc. Or any information that you can call it as we are calling it as a logical resource, right? So why we need resources? Because this entire deadlock is totally depending upon your resources. Deadlock mechanism or the deadlock phenomenon, it is totally depend upon your number of resources. Why deadlock occurs? Because there are limited number of resources and a more number of processes, and they could not get the resource. That's why the process enters into the waiting state, and as the percentage of the waiting processes increases, the definitely system enters into the deadlock state. So the resource is very important. Next, instance of the resource. So there are the resources of the type single instance here. So if I have the block, so I can draw the resource with the help of this rectangle, and the rectangle or in this box contain the one dot single instance of resource. Single instance means only one process can have access to that particular resource. And the multiple instances means, say for example, this is the box, this is the rectangle box. So if there are the multiple number of resources, I can represent multiple number of instances. So I can represent with the help of two dots. So one dot or one instance is used by the process P1, and another instance it is can be used by process P2. Means though there is only one single resource, but if it has multiple number of instances, means it is a shareable resource. Instances indicates that it is a shareable resource. So P1 and P2 it can share, but P3 cannot share because there are only two instances of the same resource types are available. But here only one instance of the single resource type R1 is available. So only P1 is able to execute that particular resource. Clear? Now the most important part is nothing but the feature or the characteristics of the deadlock. So first point is nothing but the necessary conditions for the deadlock. Always there is an examination, always there is a question. Write down the necessary conditions for the deadlock. So we have to see these are the four necessary conditions. So mutual exclusion is the first condition, hold and wait, the no preemption, and the circular wait. These are the four conditions, necessary and the sufficient condition for the deadlock to occur in the system. Meaning is that all four conditions, so all these four conditions means first and second, second and third and fourth. So all four conditions means addition. These four conditions must, if these four conditions occur, then definitely the system enters into the deadlock state. But if the operating system is able to successfully remove or stop one of the condition, if this condition is not occur, but these three conditions are there, hold and wait, no preemption, and circular wait are there, but mutual exclusion is not there, then also the system not enters into the deadlock state. Means you have to at least prevent at least one condition so that deadlock will not occur in the system. You in the sense operating system. Operating system has to prevent, or operating system has to avoid at least one condition. So if these four conditions are there, then definitely 100% means these are the necessary and the sufficient condition. If there is a ME, that is mutual exclusion, if there is a hold and wait, if there is a no preemption, if there is a circular wait, 100% the system enters into the deadlock state. And if the operating system wants that the system never into the getting into the deadlock state, it has to prevent at least one condition. At least if the circular wait it is able to stop and three conditions are there, then still we can say that there is a no deadlock in the system. Or if the no preemption condition is not occur, but three conditions are there, but we can say that yes, the system may not go toward the deadlock, right? So these are the necessary conditions. So we'll see in detail. Mutual exclusion means what? So only one process. So you know the meaning of mutual exclusion. Only one process at a time can use the resource, and if one process is requesting the resource, if another process is requesting the resource, it has to wait. So mutual exclusion means what? So say for example, process P1 is requesting some resource, but that resource is executed by the another process P2, then P1 has to wait. That is nothing but the mutual exclusion. Mutual exclusion means what? The resource is mutually exclusive. When one process is executing that particular resource, another process has to wait. It cannot execute or it cannot access that particular resource. That is called as the mutual exclusion. Hold and wait. The second condition for the necessary condition for the deadlock to occur is hold and wait. There must exist some process. Say for example, we can say this is my resource, right? And this resource is being allocated to process P1. This resource is being allocated to process P1, right? And this P1 is now requesting some other resource. P1 is requesting some other resource, that is R2. So there must exist a processes holding at least one resource. So this arrow indicates that this resource R1 is allocated to process P1. See here, but at the same time P1 is in a waiting state. P1 still wait. Why? It wait for resource. It wait to get the resource R2. It wait to get the resource R2. So there must exist a set of processes holding at least one resource. So this is nothing but the hold. This arrow we can call it as hold, and this arrow we can call it as wait. This process P1 is waiting for R2, but the R1 is already holding by the process P1. If such is the number, if this number is there, if the P1 is there, the P2 is the same way, P3 is same way. So there are 90% processes are in the same way. They are holding some resources, but they are waiting to get some resources, meaning is that they are not currently in a running state, they are in a waiting state, right? And as they hold this particular resource, so if the process P2 is there, say for example P2, and if it want this R2 R1 process, but we cannot allocate this R1 because R1 is already allocated to process P1. See carefully, yeah. If there is another process P2 and P2 want this R1 resource, but you cannot allocate this R1 to P2 because this is already allocated to resource that particular process P1. So this is the scenario that is called as the hold and wait condition. The third is nothing but the no preemption. No preemption means process cannot, resources cannot be preempted. So resources cannot be preempted, meaning is that once the resource has been allocated, no preemption, meaning is very clear to you. No preemption means what? Once the resource is allocated to the process, that particular resource cannot be preempted till its complete execution. Till the complete execution of that particular process. That is called as the no preemption. For example, if the R1 is allocated to process P1, and if it is of the kind of non-preemptive kind of resource, if this resource is of the kind of non-preemptive type, then this R1 will remains with P1 till the 100% execution of the process P1. It will not be preempted in between two process P2. It will not be removed from P1 and assigned to P2 in between till the complete execution of the process P1. Getting this point? And the third condition is nothing but the circular wait. So circular wait in the sense, so there is a circle, say P1 is waiting to get R1, but this R1 it is now allocated to, say for example, your P2 process, but P2 is waiting to get the resource that is called as the R3, and R3 is allocated to R3 is already allocated to, say for example, P1. A small circle I have drawn here. So P1 it is now waiting for R1, but this R3 is already allocated. I can say here allocated. Resource R3 is allocated to process P1, but P1 is waiting. Why? Because P1 is waiting R1, but R1 is already allocated to P2, and P2 is waiting to R3 because R3 is already allocated to process P1. So this such type of circle is there. There are the process P1, P2, P3, dot up to Pn, and these all processes they are in a circular fashion. So there must exist a set of processes P1 up to P Pn of waiting process, such that P1 process waiting for the resource held by P2, P2 is waiting for the resource held by P3, and so on. This is the way the circle, they create circle here. P2 is waiting, P1 is waiting for the resource which is held by P2, P2 is waiting for the resource which is held by P3, P3 is waiting for the resource which is held by P1, and so on. The circle completes here. So this is called as the circular wait in the system. This is called as the circular wait. So for deadlock, all these four conditions must be there. All four conditions are must. All these four conditions are must. Then and then only the system enters into the deadlock state. If either one of the condition fails here, if operating system able to avoid or prevent one of the condition, then the system will not enter into the deadlock state. But these four are the necessary and the sufficient condition for the deadlock to occur. Mutual exclusion, that is nothing but only one process at a time can use the resource, that is called as the mutual exclusion. Hold and wait, this is the hold and wait, the process holding some resources and waiting to get another resource. No preemption, the resources cannot be preempted. And circular wait, there is a circle, the processes, they are forming the circle, they are waiting to get the resources that has already been assigned to some other processes. This is the one can say this is nothing but the concept of the circular wait. So remember the four condition and understand the condition, necessary condition for the deadlock, right? So we'll stop here for the today's lecture. So what we learned in the this particular lecture, the concept of semaphore, the classical problems of synchronization, or the classical examples, or the classical types of synchronization, how the synchronization is achieved, and the important, very basic concept is nothing but the necessary condition for the deadlock to occur. And the question that may ask in the in-semester as well as the end-semester examination on the concept, first part of the unit number 3, that are the explain with the definition the concept of semaphore. You have to write down in detail how the semaphore works with the help of signal and wait function. Write a semaphore solution for a dining philosopher problem. Another question, a very important question. Write a structure of reader-writer problem in bounded buffer problem using semaphore. Again, same case, the reader-writer problem with the help of your semaphore, you have to write the pseudocode. In both this case, whether it is a dining philosopher you have to write down the pseudocode, as well as in the ReaderWriter problem, you have to write down with the Semaphore pseudocode, right? Both cases we are using the Semaphore concept. The third one is the explain the necessary and the sufficient condition, the 4 condition which we discussed just now, that we have to elaborate in detail. Mutual exclusion, old and wait, no preemption, and final is the circular wait condition, right? These are the reference book. Always from the first lecture, I am asking that you have to refer the reference book only. Don't go for any local author. So reference book are the best to clear the concept. So for this today's lecture, thank you. We'll stop here.